Welcome to 2.4 complex numbers. Complex numbers and imaginary numbers where the imaginary number I is equal to the square root of -1. It opens up a whole new world for us, and a great question would be, well, why would we ever need to talk about imaginary numbers? There are some actual real-world applications, including in electrical circuits, and we'll be talking about those a little bit, but we're just going to go through the mechanics, and I don't think that this is going to be a particularly challenging section for you if you get through the homework with it. So if A and B are real numbers, numbers that we're used to working with, then the number A plus BI, or A plus B times square root of -1, is a complex number. And it's said to be written in standard form, A plus BI. If B equals 0, then we're just dealing with a real number. And if A equals 0, then we're just dealing with a purely imaginary number. Okay, pretty simple other than the whole concept of the square root of -1, a number times itself equals -1, and that is I. So we would say that I squared equals -1, and that opens up a world of mechanical possibilities for us, computational as well. All right, equality of complex numbers. In order for two complex numbers to be equal, the real portion, A and C, have to be equal, and the imaginary coefficient have to be equal. So it's kind of like two separate entities, each having to be equal. The real parts are equal, imaginary coefficients are equal. Likewise, when we add two imaginary numbers together, we just add the real parts. So we're going to add A and C together, and we would add B and D together for some of our imaginaries. Pretty easy, and difference is just as you would expect. And because we can write the square root of -A as square root of -1 times A, that could be thought of as square root of -1 times square root of A, and that could be I root A, or square root of AI. Make certain that we don't allow this square root sign to migrate over that I. Okay, so as I said, mechanics, I think you're going to find these not to be particularly challenging. I'm going to get zoomed in here a little bit so you get a good look at these. Let's see, I can do this. And here we go. Find a real number A and B such that the equation is true. Well, if these are going to be equal, then A plus 6 has to equal 6, and A is 0, and 2 times B has to equal this sneaky -1 out in front of here. So we've got 2 times B equals -1, or B is -1/2. So there's our real numbers that make the statement true. Pretty simple compared to what you guys are used to doing. Write a complex number in standard form. So this is 7 minus the square root of 25 is 5, and the square root of the -1 that we're seeing, or that we can imagine in front of there, is I. And it is that easy. And that is in standard form. That's in A plus BI form. Okay, now here's a purely real number. To write it as a complex number in standard form, we would just write it as -3 plus 0I. Okay. I squared, as mentioned above, is equal to -1. So we end up here with 2 times -1, -2 minus 6I. Right? Number 18, I'm just going to drag this along to the side. I'm going to leave this -I. This becomes minus. This would be, I'm going to pull the I out of here first, and in class I'll talk about the Bluegill theorem that I sort of invented. But this would be I times square root of 23 squared, or equals -I minus, when I square I get I squared, that's -1. When I square 23, the square root of 23, I get 23, so cleaning this thing up, I end up with a positive 23 is mixed with a minus I. So there we go. Okay, and then this last one, I know this is going to be I times the square root of 0.0004, and if we had to, we could jump to calculator on that. But square root of 4 is 2. I just need some decimals. Let's see. How about if I get, what if I was to take 0.02 and times 0.02? I'd need 4 decimals and a 4. And I've got 1, 2, 3, 4 decimal places and a 4. So this is just equal to 0.02i. However, in standard form, that would be 0 plus 0.02i. This is purely imaginary. We won't typically leave answers like that, but because they said in standard form of a complex number, in a couple cases we're going to include some zeros here. Okay, addition and subtraction couldn't be easier here. This is going to be 11 minus 2i, distribute the negative, plus 3 minus 6i. And you can, in this case, just treat i's like variables. In fact, in all cases you can, other than when we get I raised to a power, as you'll see shortly. So I end up with 14, plain old 14, and minus 8 i's. And let's see here. So this is going to be 22 plus negative, that's minus 5, plus positive, that's plus 8i, minus 9i. And we just combine the real parts. 22 minus 5, 17. 8i minus 9i, that's a minus I. Pretty simple. Okay, now I've got some good news on this coming up, because your calculator will actually do some of this for you, but we're going to do it by hand. But just for the sake of it, I'm going to show you this. Let's quit out of here. You can actually, you've got an I down here at second dot. You know what? I'm videoing this, and I'm not certain that this Smart View calculator is going to show up here. So I'm going to back up on that and run one through my. Sorry, there should have been a calculator showing there when I slid the paper over, but I don't think you guys get to see that. So I'm going to pull up actually a handheld calculator here, and we're going to go through this. I'm going to refocus here just for a moment. Try to refocus here just for a moment so we can see the paper, see the calculator. And let's go with that. So in here, as you can see, hopefully you can see decimal point. There's our I right there, so that's second decimal point. So I'm going to go ahead and enter this equation, parentheses 6 minus 2, second hit decimal point. There's my I, close parentheses, parentheses 2 minus 3, second decimal point, I. It actually does it for us. But we're going to go ahead and go through by hand, but eventually you're going to get freed up, and maybe even some of this assignment in a little bit, I'll free you up to let you use a calculator on. So it's nice to check, but you're going to have to show me at some point you can do this by hand, and that would be in the form of a quiz problem. Okay, so by hand, no different. We're just going to FOIL. I get a 12. I get a minus 18i. I get a minus 4i, and I get a plus 6i squared, but 12, I squared is negative 1, so this is really minus 18i minus 4i plus 6 times negative 1 minus 6. So I end up with 6 and minus 22i, just like we saw when we did this on calculator. So for 40, you might want to write this out. 5 minus 4i times 5 minus 4i. FOIL, 25 minus 20 i's minus 20 more i's minus 40 i's, and minus times minus plus 16i squared. And that is 25 minus 40i minus 16i squared being negative 1. So we end up with 9 minus 40i. Okay. Conjugates of complex numbers. This becomes important when we're going to simplify something like this. We want to simplify something like this in 56, or even truthfully in 52. Write the conjugate of the complex number. Well, our conjugate is negative 4 plus root 3i, as we know. And because number 48, we'll come back to this, because number 48, this could be written as 0 plus square root of 10I. The conjugate is 0, should have put that down here, conjugate is 0 minus root 10I. That's our conjugate, or just negative root 10I. Okay, and then multiply the number by its conjugate. So negative 4 minus root 3I times negative 4 plus root 3I. And I think we know when we multiply conjugates in the past, good things happen for us. Excuse me. Okay, so let's go ahead and FOIL. I get positive 16. I'm going to get, check it out, a minus 12 or minus 4 root 3I, but I get a plus 4 root 3I. Those cancel. And then I get a minus times plus minus root 3 times root 3, 3, I times I squared, but I squared is negative 1, and I end up with 16 minus 3 times negative 1, or 16 plus 3, 19. Oh, so you may see the benefit in multiplying by conjugates at times. So in this case, my original number was root 10I, and that's just being multiplied by the conjugate, negative root 10I, and that gives me positive times negative, negative, root 10 times root 10, 10, and I squared, which is negative 1, for a final answer of 10. That's really just mental or just complex number gymnastics right there. So why would we do that? Well, just like radicals, it's not considered proper form to leave i's in denominators. So in this case, if I multiply by the conjugate here and the denominator, which would be negative 2i, it would cancel that. But because this isn't a binomial, I could just multiply by I on I. And that gives me negative 5i on 2i squared, which is negative 5i on 2 times negative 1, negative 2, for a final answer of 5/2 I. But 56 is where the conjugate really becomes useful, because I can't multiply by I on I here and get rid of i's in denominators, because when I distribute it, I'd have 1i. So I'm going to multiply this by the denominator's conjugate. We've done that before, maybe just not with complex numbers. 1 plus 2i on 1 plus 2i. And here's where your calculator is really helpful, and I'll free you up to use your calculator on some of this, but we're not going to here. So I'm going to FOIL the top. I get 8. I get plus 16 i's minus 7 i's. Plus 16 i's minus 7 i's. That's plus 9 i's. And I ultimately get a minus 14 I squared. In the denominator, I get a 1. I get a plus 2i and a minus 2i, cancel, conjugates, and I get a minus 4i squared. So cleaning that up, this is 8 minus 14 times negative 1, or 8 plus 14, 22 plus 9i, all on 1 minus 4 times negative 1, that's 1 minus negative 4, that's 1 plus 4, for a final answer of 22 plus 9i on 5. But again, the good news is, if you're freed up to use your calculator, you could just enter that, and it would simplify it into this. It may give it to you as 22, it may give it to you in this form, which is even better, 22 fifths plus 9 fifths I, because now it's in standard form. I don't recall on your calculator. It might do this, and you just have to split them. Okay, 5960, perform the operations and write the results in standard form. Again, your calculator will do this. But if I was adding fractions, I would need common denominators. So my least common denominator needs a factor of 2 plus I and a factor of 2 minus I, which means this 2i, the first term, had to be multiplied by 2 minus I on 2 minus I. And the plus 5 had to be multiplied by 2 plus I on 2 plus I. So let's see what happens here. I get a 4i minus 2i squared plus distribute the 5, 10 plus 5i, all on FOIL 4 minus 2i plus 2i minus I squared. So let's see, in the top, real parts. Is it clear? I hope it is. Minus 2i squared is minus 2 times negative 1. That's 2 and 10. So these are real. 10. My imaginary is 4i's plus 5i's plus 9i. In the denominator, I get 4 minus negative 1. 4 plus 1, 5. And that's probably a decent answer at times, but if we want it in standard form, we split the real parts. So this becomes 10/5 plus 9/5 I, or 2 plus 9/5 I. Not too bad. In 61 to 70, now what your calculator will not do, well, you know what, maybe it does, and I'm underestimating your calculator, but I don't think it will simplify this and pull the I out. I think it will just give you an error. Maybe there's, you know what, there might be a setting you can go to, but I haven't done that. In 61 to 70, perform the operation and write the results in standard form. So first thing I'm going to do is pull the I out. I've got the negative 1, square root of that is I. And then 50, I could think of that as 25 times 2. I think you see the benefit in that. Plus, pull the negative, square root of negative 1 is I. 25 divides this. How many quarters are there in $2.75? Be 12 quarters and 3, so it's times 11. So this could be written as 25 times 11. And I end up with 5 root 2i plus 5 root 11i. And if we're supposed to write that in standard form, this is not, but I could write this as 5 root 2 plus 5 root 11 times I and put a 0 plus in front of it. Kind of sneaky. Okay, number 70. I'm going to take care of the my bluegill theorem that I'll talk about in class. I'm going to pull the i's out first. You might have an idea where that's going to. So I get 3 plus 5i times 7 minus, root 5i, excuse me. 7 minus root 10i. Foiling, I get 21, first times first. Outsides, I get minus 3 root 10i. Insides, I get plus 35. No, I don't. I get plus 7 root 5i, sorry. And last times last, I get minus 5 times 10 root 50i squared. Okay, we got some cleaning up to do here. So I've got a 21. That's real. This minus root 50i squared, I think I'll clean that up first before I talk about that. Minus 3 root 10i plus 7 root 5 with an I. This would be minus, but I squared is negative 1, so plus, and square root of 50, just like we saw up in number 62, is that's square root of 25 times 2, or 5 root 2. So if I group my real parts, I've got 21 plus 5 root 2. There's my real part first. And then my imaginary part could look something like this. I could go plus negative 3 root 10 plus 7 root 5 times I. And we may make this minus, and this would be positive negative. But that's where we're at on that. Once again, calculator will do these for you, but for the purposes of this assignment, want problems by hand, and let's take a look at one last problem. In exercise 71 through 82, solve the quadratic formula, or quadratic equation. Factors of 10 that add up to 6, we don't have them. I didn't expect them because I think I know where we're going here. So, x equals the opposite of b, plus or minus square root b squared minus 4 times a times c, 10, all on 2a, or Negative 6 plus or minus. Let's see. This is 36 minus 40. Negative 4 all on 2, which means this parabola that passes through 6 and is going up real steep, or excuse me, passes through 10 and is going up steep with a slope of 6 and is cupping up because it's a positive parabola, it means it never made it down to the axis. There are no real intercepts. However, negative 6 on 2 plus or minus square root of negative 4 is 2i on 2. Tells us in imagination land our solutions are negative 3 plus or minus I. And there you have it. Strictly mechanical, nothing real worldy yet, but we will talk about some real world properties of imaginary and complex numbers. Good luck. Make sure you're asking questions if necessary, and we will see you soon.